Welcome to concavity of parametric curves. So recall, to determine concavity, of a curve in the xy plane. We needed to find the second derivative. Right? So general idea with parametric curves is we also need to find dy dx. So if we're working sorry, not dy dx, the second derivative, d squared y dx squared. If we're working with parametric curves, or with a parametric curve, given by x equals f of t and y equals g of t, then we need to find the second derivative, so d squared y dx squared. But dy dx is a function of t. So we can't just take the derivative with respect to x. So it's not as simple as taking the derivative with respect to x of dy dx. Instead, we again use the chain rule. So what we can do is we can definitely take the derivative with respect to t of dy dx, since dy dx is a function of t. This derivative should be equal to the derivative with respect to x of dy dx times the derivative with respect to t of x, or times dx dt. So this gives us then the derivative, the second derivative of y with respect to x should be equal to the derivative with respect to t of dy dx over dx dt. Or in other words, the derivative with respect to t of g prime of t over f prime of t. That whole thing over f prime of t. So for example, let's consider the parametric curve given by x equals t squared and y equals sine of t. And our job is to determine the concavity at the time t equals pi over 3, and then find at least some of the points of inflection. So we have that dx dt, again, was 2t. dy dt is cosine of t. So we have dy dx is cosine of t over 2t. This means that the second derivative should be equal to the derivative with respect to t of cosine of t over 2t. That whole thing divided by dx dt, so divided by 2t. So we are looking at, we have a quotient rule here. Derivative of cosine is negative sine of t times the denominator, so times 2t. Then we subtract off cosine of t times the derivative of the denominator, so times 2, all over the denominator squared, so all over 2t squared. Then we divide by another 2t. So this becomes, I'm going to pull a negative 2 out front. Then we have t sine of t plus cosine t up top. And then we would have a 2t squared times another 2t in the denominator, making 2t cubed or 8t cubed. So this becomes a negative t sine of t plus cosine of t all over 4t cubed. So at t equals pi over 3, we have d squared y dx squared would be equal to a negative, and then pi over 3 times sine of pi over 3 plus cosine of pi over 3 all over 4 times pi over 3 cubed. So this is a negative pi over 3 times sine of pi over 3 is root 3 over 2. Then we have plus cosine of pi over 3 is 1/2. All over 4 pi cubed over 27. This is a negative value, it's less than 0. So since d squared y over dx squared is less than 0, then we get concave down. Finally, we are asked to find the points of some points of inflection. So for our points of inflection, the points of inflection occur where the second derivative changes sign. So this would be essentially, let's look for where the second derivative equals 0. And is hopefully changing the sign. So essentially for this, we are looking for t sine of t, or negative t sine of t plus cosine of t, all over 4t cubed. Is that equal to 0? So this is equivalent to looking for where t sine of t plus cosine of t is equal to 0. This is technically equivalent to t equaling negative cotangent of t. That's not an easy equation to solve. So we'll just use decimals to find these. So if we switch over to decimals, if we enter, I'm going to do it in terms of x instead of t. If we enter x, sine of x plus cosine of x, we can see quite a few places where that's changing sign. And so the first place is at about 2.798. The first positive location is at about 2.798. Again at 6.121. Again at 9.318. Again at 12.486, etc. Right? So if we transfer that back to our notes, this is the graph of t sine of t plus cosine of t. Okay, so we've got our various places where it changes sign. We have points of inflection. At t equals 2.798, t equals 6.121, t equals 9.318, t equals 12.486, and then it would continue going beyond that. But these are some of the locations for the points of inflection. So that is concavity. In our next video, we will start doing some tricks with integration for parametric curves. So next video, we will take a look at arc length, and then we will finish up with surface area of a rotational solid.